Hello, good morning, everyone. I'm glad to see you all here. It's already 9 o'clock according to my computer's time. It's time to begin our lecture number 15. And this would have been our last lecture, hadn't we skipped one lecture. So today I have planned a lecture about the Schwarzschild metric, Schwarzschild solution, its geometry, its properties, and this will be mainly a Blackboard lecture with a little bit of help from a Python Jupyter notebook and also just a handful of slides, but we'll mainly work on the Blackboard, which has the advantage that I'll be able to show you all the derivations of the results I'm discussing. Before we do it, I would like just to give you a little bit of correction of what we did last time. So I had a closer look at our slides and our derivations, and it seems that there were some small mistakes there. So I just want to point them out for the future reference. If you try to learn something from this lecture or learn to the exam. When we talked about gravitational waves during the last lecture and discussed the total emitted energy, I showed you that we should integrate the total power of the gravitational waves emitted by summing the flux of both polarizations. But if you integrate over a large sphere, obviously you need to include also the radius of the sphere squared as a part of the area form. Everything else is okay. And then on slide 127, we take the trace, so h bar traceless transverse ij, the perturbation of the metric from this type of two orbiting masses. Well, it's the transverse traceless part of the tensor consisting of this diagonal with cosine 2 omega t and additional coefficients here, but these coefficients are not relevant when you pass the transverse traverse gauge. They will be projected out and will be just left with the trigonometric functions and zeros, and that's it. Just for future reference. And then there's also small things on on the Blackboard number 3 from the previous lecture. It's a trivial thing. We have shown that an identity that 2kl plus a divergence is equal to the second time derivative of t00 xkxl. So if we plug it into the formula for the perturbation of the metric from a gravitational wave, there should be a second derivative over here. And there is also a coefficient missing here, but that's irrelevant because this thing is 0 anyway. So there is this small thing over here. When we derive the quadruple formula, there's here the second derivative missing. And on slide number 4, this derivative appears here, but only as the first one. There should be a square here, and a square here. And that's all I noticed. These are small mistakes I've made. I uploaded the corrected versions of these slides to the web page, so you can download them if you wish. Okay, and I think it's time to move to the lecture itself. Okay, so during the last lecture, we have introduced the Schwarzschild solution. Yeah, right here. As the solution describing a spherically symmetric body and its gravitational field outside that body, or a black hole without a spin, although we haven't defined a black hole yet. We have spelled out the assumptions that the spacetime is spherically symmetric, static, and it's vacuum. We have sort of guessed the form of the metric, which is consistent with the assumptions, then imposed the Einstein equations on this form of the metric. And then it turned out that after a small adjustment of coordinates, we can find the solution to look pretty much this way. So this is the Schwarzschild metric. It contains one parameter Rs. We will now figure out what exactly this quantity means. It has 4 independent Killing vectors corresponding to the time translational symmetry and the symmetries of rotation with respect to the axis x, y, and z. It has 2 singularities at r equal to 0, just like the Minkowski space, but also at r equal to rs. So if rs is positive, there is another type of singularity over here. And we also noted that if r approaches infinity, so we are moving away from the object we describe, the metric basically reproduces the Minkowski metric, except that it does it in the spherical coordinates. So very far from this heavy center, the metric looks pretty much like a closed one. And there's a more precise definition, but roughly this means that the metric is asymptotically flat. There are some more stringent conditions on how quickly this fall off actually happens, but they're not really important now. And now, during this lecture, I would like to begin by analyzing more in detail what the metric appears like when r goes to infinity, and we'll do it on the blackboard. Okay. So we go here. Oh, that looks ugly. Okay, let's do it this way. This down here and this up here. Okay, so the topic is Schwarzschild metric for r going to infinity. Now, what I want to prove today is that in appropriate coordinate system, this metric can be written, the Schwarzschild metric is basically the Minkowski metric plus a Newtonian perturbation. And zeros everywhere else. And higher order terms which are irrelevant when we go with r to infinity. So it's not only that that the metric reproduces the Minkowski metric, actually it reproduces the Newtonian perturbation of the Minkowski metric first, and then the Minkowski metric. And this happens in appropriate coordinates. Okay, so we begin by recalling the Schwarzschild metric as it has been defined. So Rs is called the Schwarzschild radius, and it's a dimensional quantity of the dimension of length. It probably informs us about the size of the object somehow. And that's the metric tensor. I'll be using, and this is a fairly standard notation, d omega squared to denote the metric on a sphere. Okay. Now, your first guess might be to simply introduce a quasi-Minkowski coordinates simply by imposing, so the first guess. So we write that x is basically r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r cos theta. And then we pass to the standard coordinates, but it turns out that it doesn't work. And the reason why it doesn't work is that if you do it, what happens is that indeed the metric sort of looks like Minkowski, we will not perform the full calculations, but you can spot it if you look carefully. So dr squared will then change into dx squared plus dy squared plus dz squared. But so this and this and this will produce basically this flat metric. But then note the perturbation here has the form of minus rs over r of plus rs over r, and here we will have dt squared. Here we have dr squared with a roughly with a minus, now with a plus. But this thing here is not dx squared plus dy squared plus dz squared. So this looks like a very nice candidate for the Newtonian potential, but this perturbation over here does not really appear like a fully diagonal matrix. It only has the two first entries. But the reason why this happens is that we are using the wrong radial coordinate. So let's change the radial coordinate first. And we want to change this radial coordinate for very large r, but not by very much. So we introduce a new coordinate r tilde or tilde, such that r is equal to r tilde plus a plus something that is of even lower order in r than before, so r2 minus 1. So you can think that we write the old coordinate in terms of the new coordinate, but as a series in 1 over r, which begins with r bar or r tilde. And we can also write it in the following form. This is 1 plus a over r tilde plus o of r to minus 2. And this is multiplied by r tilde. In this form, it's clear that the new coordinate is designed in such a way that it very closely matches the old one for very large r, but for somewhat smaller r, there's an additional term appearing here. A is a constant, by the way, which we haven't specified yet. And we will specify soon. Okay, so we would like to express our metric in this new coordinate r bar. What are we going to need to do? Well, we've got terms like rs over r, which we'll have to re-express using r tilde. We have dr squared and r squared, which we'll also have to express via the derivative or the gradient and the value of r tilde. So let's do it. We begin by dr. So dr, we can use, for example, we can use the left formula because then things are very simple. You got dr tilde here, this gives 0, and this gives something of order of r to minus 2 dr tilde, or this is dr tilde 1 plus o r tilde to minus 2. So the derivatives of r and r bar are very close to each other, basically identical, except for something of very low order. This is because this difference here is a constant, so constant does not contribute to d. So it will be fairly easy to substitute the r tilde here. Then let's go to page number 2, Blackboard 2. Then we have terms like rs over r, which is rs over r tilde plus a plus o of r minus 1, which is rs. Again, we need asymptotic expansion in case r tilde and r go to infinity. And what we get is plus o of r tilde to minus 2. Yeah, and we can use the Taylor series for 1 over 1 plus something over here. That's 1 minus a over r tilde plus O of r tilde to minus 2. Or if we just keep the lowest order, this is just rs over r tilde plus O of r bar to minus 2. Okay, so this is basically conserved. And then finally, we need r squared, which is r tilde squared 1 plus a over r tilde plus r tilde to minus 2. And this is squared, which is r bar squared 1 plus 2a over r bar plus O of r tilde to minus 2. Okay. And now the trick is simply to substitute that over here. So the metric becomes minus dt squared 1 minus rs over r tilde plus a higher order term. We can keep them for the sake of bookkeeping. Then we've got dr bar squared 1 minus rs over r bar plus this higher order term to minus 1. And there is, if you recall, another r to minus 2 term from passing from dr to dr tilde, plus there's r tilde squared 1 plus 2a over r tilde plus higher order terms. And here we got the omega squared. Okay. So let's write it this way. 1 minus rs over r tilde plus the r bar squared. This is inverted, so we get here 1 plus rs over r. And then we get uh, 1 plus 2a over r tilde r squared, the omega squared. And we were missing all the time terms of the order of r to minus 2. So there's a tensor of the order of r to minus 2 in terms of all these things here still missing. Okay, so now it's time to pick our rs. And look, here we add rs over r. Here also we add rs over r. So let's take a to be rs over 2. And in that case, if we pick this constant, so the Schwarzschild radius divided by 2, we get minus dt squared 1 minus rs over r bar plus dr or dr tilde 1 plus rs over r plus 1 plus rs over r tilde d omega squared. And now in this form, when we pass to the quasi-Cartesian coordinates x, y, z using the standard form of the spherical equations, it turns out that what we get is minus dt squared plus dx squared plus dz squared plus dy squared plus rs over r, and here we get dt squared plus dx squared plus dy squared plus dz squared plus higher order terms. Okay, that's nice. And now it remains just to recognize that this thing here, we can call it minus 2 phi, the Newtonian potential. And in that case, we recover the metric exactly in the form I announced just a couple of minutes ago. So the metric is the flat spacetime metric plus a diagonal made of the Newtonian potential. Just right here. So we recognize that the phi, the potential, is equal to minus Rs over 2r. Okay, that's very nice. But, and look, this was exactly like the Newtonian potential from a single body of a particular mass, namely of the mass of minus gm over r, provided that we identify the coefficients. So this is the Newtonian potential from a single body of the mass m very far away from this body. And these two type of things, we expect them to match because Schwarzschild is supposed exactly to represent a massive body. So very far away, the metric looks exactly like a Newtonian perturbation of the flat metric with the mass equal to gm equal to minus plus rs over 2. Or conversely, we discover that rs, the Schwarzschild radius, is just 2 gm, where m is the mass of the body. So if we measure the mass of the body at infinity, for example, by tracking a body orbiting around this central object, by watching its motion, the period, so for example, the orbital period, the velocity on the orbit, it's possible to reconstruct the orbit and the central mass, and the central mass is exactly going to be this m related to the Schwarzschild radius by gm equal to rs over 2, or rs equal to 2 gm. The bottom line is that the metric, the Schwarzschild metric at very large distances not only behaves like the Schwarzschild, it behaves like the Schwarzschild plus a Newtonian perturbation from a central massive body m, and there's a relation between m and the Schwarzschild radius. Do you have any questions to this? Okay, if not, then let's go to the slides. Annotations. Now this is visible. Okay, so this metric, let's go harder. So it's much more common to use the mass itself as the parameterization of the Schwarzschild metric. So instead of rs, people very often use 2gm. So this is this prefactor here is 1 minus 2gm over r. Or if people move to the geometrized units, then instead of g is not needed here, and what you simply have is 2m over r and 2m over r right here. This is a much more common version of the Schwarzschild metric, and the one you're likely to encounter in the literature. So people don't use the Schwarzschild radius all that much, actually. We prefer to express the one parameter of the Schwarzschild family by the mass of the central body, which we assume to be positive. Okay. So let's go back to the here. I will now, let's go to the next page. So there is a couple of classic tests of relativity Einstein already proposed when he derived GR in early 1910s and 1920s. One of them is the frequency shift of photons in a gravitational field. We have already derived the appropriate expression for this quantity, the frequency shift in the Newtonian approximation, but here with the help of the Schwarzschild metric, we can derive a more general expression, which is valid outside the validity regime of the Schwarzschild, of the Newtonian approximation. The Newtonian approximation for Schwarzschild works only very far away from the central body. Close to the central body, the metric is so far away from the flat one that we need to use a bit of a different approach. Okay, so frequency shift. There is something very important. So the formula we'll derive is important by itself, but it also tells us a little bit more about the singularity structure of the spacetime. So I write our metric already in our new parametrization. Recall that we use C equal to 1, so this product G times M has the unit of length. 1 over R minus 1 d R squared plus R squared d omega squared. Now we introduce static observers, so observers which are aligned along the integral curves of this time-like vector field. So these are observers who remain at rest with respect to the black hole. They neither rotate around it nor perform any radial motion. So let's calculate the forward velocity of such observers. Obviously, they can only have a component in the time-like direction, so let's call it u0. We know that g mu nu u static nu needs to be -1. That's the normalization condition for velocity. There is no motion in the radial or in the azimuthal directions. So what we get is -1 minus 2gm over r u naught squared is supposed to be equal to -1, which means that u naught, it actually depends on r, where we put our observer. That's 1 minus 2gm over r to the power of -12. Again, that's something that diverges as r approaches the 2gm or Schwarzschild radius singularity. Okay, now let's consider propagating photons. So we will use the following facts, just like we did in the Newtonian approximation. So the metric has a time-like Killing vector, T mu equal to 1, 0, 0, 0. We know that this is 0. And in that case, we know that for every photon, we have P mu, T mu equals to minus energy, conserved energy, this is constant. We have proved that for a photon undergoing a geodesic motion, this product, which we call the total energy, is conserved. Okay, but what we want to compare is this type of product at the emission point, and also this type of product, let's call it energy as mentioned by the stationary observer at some emission point RE, and the same guy at the observation point, which we assume to be at a different radius. And this is again the energy according to the stationary observer at point RO. So we know that minus p mu u stationary mu, that's minus p mu. Okay, so from this thing over here, we see that u stationary mu is nothing else but 1 minus 2 gm over r to the power of minus 1, 2 of the scaling vector t mu. So they're very close to each other, but not identical. They differ. The forward velocity of a static observer differs from the Killing vector by a normalization factor. Okay, we can take this into account. So this is t mu 1 minus 2 g m over r to minus 1/2. And that's the energy at radius r. This guy is conserved. So when we calculate the ratio, so the redshift is defined as the ratio of the energy by the stationary observer at the emission point divided by the same thing at the observation point. We can plug in the formula over here, use the fact that this is constant in both expressions, and what we get is just 1 minus 2 gm over RE, 1 minus 2 gm over RO, to the power of 1/2. Or to say the same thing differently, the energy as observed by the static observer at radius RO is the energy as registered by the emitter at the radius RE multiplied by 1 minus 2 gm over RE, 1 minus 2 gm over RO, to the power of 1/2. Now, you can easily check that this formula is perfectly consistent with the Newtonian approximation we considered before. So if we go with r to infinity, this 2 gm over r is just the Newtonian potential, and you'll be able to see that the difference of energy is exactly given by the relative difference of energy is given by the difference of Newtonian potentials. But this formula in this form is also applicable for very small radii, for which the Newtonian approximation doesn't work. And it's also very interesting to see what it actually predicts. Okay, I will use a bit of a different color. So assume we fix the observation point at some RO. But we take the emission point, approach the 2 gm radius from the above. So we allow the emitter to be as close as possible to the r equal to 2 gm singularity. And what happens in this case, it's easy to see. The denominator is fixed, but what happens to the numerator is that it approaches to 0. So the energy as observed by the observer of a photon emitted with some kind of energy is decreasing to 0 as the emitter is approaching this singularity. So when you have an emitter which is very close to this singularity, everything they send to us appears to be very strongly redshifted. And formally at r equal to 2 gm, the redshift is so large that the energy is actually 0. We don't get any photons. So there is something very interesting going on when we approach this r equal to 2gm limit, every information sent by a static observer from this part appears to be extremely strongly redshifted. And let's see vice versa what happens. So we fix the emission point at some finite RE, but we put our observer at RO, which is approaching 2gm from the above. And in that case, something else happens. The numerator is fixed, but the denominator is approaching 0. So the energy as observed by the observer diverges. So we can imagine the r-axis. This is r equal to 0. This is the strange second singularity r equal to gm. We considered a fixed emitter here, but an observer which is very close to here. And any photon sent from the emitter to the observer will appear to be extremely blue shifted. And as we approach r equal to the gm, a static observer will see an infinite blue shift. So there is something very interesting going on. Any photons coming from the outside to observers close to r to gm appear extremely blue shifted. On the other hand, any photons sent by these observers will appear very strongly red shifted by everybody else. So do you have any questions to this derivation? I don't hear any, so let's go to the next topic. There's obviously something very interesting going on with this r equals to tm surface, but that's not the only thing. Let's now have a look at the static observers themselves. So, as you know, in a gravitational field of a single body, it is impossible to suspend something at a finite distance from the central mass without an engine. You need a force to oppose the gravity. So if we have our situation, our central body, this is r equals to 2gm. And if you want to have a static observer, which is neither orbiting this body nor performing any radial motion, we need a force which opposes the pull of the gravity of the central body. And this is easy to check. You just check that a body which has a finite and not changing distance undergoes some kind of acceleration. This acceleration needs to be due to some kind of force. And we can check how big this acceleration is. Obviously, in the Newtonian case, this is just 1 over r squared law. You need a force proportional to 1 over r squared in order to keep your body at rest. Let's see what happens in the Schwarzschild case. So what we want to derive is basically the derivative of the static field with respect to the static field itself, which is basically the u static mu over d tau plus gamma mu alpha beta u static alpha u static beta. A static observer is static. It has its for velocity does not change with time, so this is equal to 0. So this acceleration, let's call it a static mu, is just equal to gamma mu alpha beta u static alpha u static beta. But then we know that u static has only the has only the first component non-vanishing and equal to 1 over 2gm over r to the power of minus 1/2. So what we get here is 1 over 1 minus 2gm over r to the power of minus 1 times gamma mu 0, 0. The gamma mu 0, 0 component. Okay, so that's something we can in principle calculate. But in fact, there's hardly anything we have to calculate. And here Here is why. What kind of components is the acceleration allowed to have? Can it have a radial? Can it have non-radial components or transverse components? The answer is, of course, no, because this is a spherically symmetric situation. Any kind of transverse component of this force would be incompatible with the full spherical symmetry of the situation. So what is left is just the time-like component in the t direction or the radial component. But we know from the relativity course, elementary part of that, I think first or second lecture, that this acceleration vector has to be orthogonal to u itself. But that means that there is no time-like component of this acceleration vector allowed either, because u has a non-vanishing tidal component and nothing else, so this product will not be zero. So a mu static can only have the radial component. A1 static in the direction of r. So let's calculate that. A1 static is 1 minus 2gm over r to minus 1. And we need gamma 1, 0, 0. It's just one Christoffel to calculate. In principle, it's a good exercise to calculate all the Christoffels of the Schwarzschild metric, but for the sake of time, I will not do it here. But this one is something we can easily calculate. So gamma 1, 0, 0, that's 1/2 G11. And here we'll have G010 plus G010. So we are switching the order of these two indices, but they're the same index, so who cares? And then we have G001. Now we need to go back to the form of the Schwarzschild metric. And what we see is that we have only so the components, this is a diagonal metric, so there's no 0, 1 components here. So this is 0, because there are no off-diagonal components. We are just left with G00 divided by 1. Okay, G upper 1, 1. That's 1 over 2 gm over r, but without the minus 1, because we are looking at the inverse metric. And then G00 over 1, that's just d over the r of 1 minus 2 gm over r, which is 1/2 1 minus 2 gm over r. And from this we get plus 2 gm over r squared, which is equal to gm over r 1 minus 2 gm over r. Okay, so that's our Christoffel. So we plug in the Christoffel into here, and we get that A1ST. This will cancel out this one, is equal to gm over r. Okay, so superficially we have recovered exactly the Newtonian value. It seems that there is nothing interesting happening. But keep in mind that this is a little bit misleading, this statement. The fact that in a particular coordinate system we get the same expression doesn't mean very much in relativity at all. It's not a physical, the component in an unspecified coordinate system is not by itself a very physical quantity. And keep in mind that the metric is very far from the standard one. So we should be careful with our intuitions. Instead of calculating the components, let's try to calculate the magnitude of this vector, which is the square root of G mu nu, A nu, A nu. That's a physically relevant quantity. And if we plug in this thing over here, what we get is Gm over R. But then the one component of the metric tensor, or rather its square root, contributes 1 minus 2Gm over R to the power of minus 1/2. So the physical thing, the magnitude of acceleration we need, is actually this thing over here. This is a non-physical thing which just by accident appears to match exactly the Newtonian approximation, but the physical value of acceleration this observer undergoes, which is related to the physical value of the force we need to exert in order to keep it in one place, is this thing over here. And this guy here, unfortunately, diverges as we approach the R equal to Gm surface. Meaning, as we approach the surface, it becomes more and more difficult to keep our observer at a given place. We need to apply an ever more increasing force, and it becomes entirely impossible if the bodies at the surface are equal to Gm. It's simply impossible to keep it in place. Of course, we could try to do something else. Instead of trying to keep it by force at one point, we could try to maneuver our object into a circular orbit around this body, and then still the radius will be constant, and we'll do it probably during the next lecture. But at the moment, I just wanted to point out that it's impossible to keep your observer static at this surface R equal to Gm, and it becomes increasingly difficult when you approach the surface. So this blow-up is quite interesting, the blow-up of acceleration. Have you got any questions? I didn't hear any. Okay, so the next big topic we will discuss will be the geodesics in the Schwarzschild solution, or geodesics in the Schwarzschild metric. This is a very big topic, but also very interesting, and it's absolutely important to, it's absolutely crucial to understand how they behave. If you have any, if for some reason you want to understand the behavior of the physical properties of the solution, because in the end, the way we probe the universe in astronomy, astrophysics is by tracking the motions of massive and or bodies, or observing the influence of these masses on the light propagation via lensing. And this is all encoded in the structure of geodesics in the Schwarzschild spacetime. So this is a topic we will spend some more time on, because it's simply quite important. Just to tell you more or less what the idea is, we already know that very far away from this massive center, the metric behaves pretty much like the Newtonian approximation, with the potential given by the 1 over R law. So we can expect that everything will be consistent with the 1 over R squared law of the Newtonian gravity. We'll be able to use the results of the Keplerian motion. The orbits of bound particles will be ellipses or circles with the well-known scaling laws for the period and the 7 major axes of the orbit. But as we approach the center, the orbits become increasingly distorted. They start to behave somewhat differently than expected, and we will see exactly where these differences come from and what they look like in a second. But before that, let's have a look again at a few slides I have shown you. I have prepared. So this is the Schwarzschild metric. Using the variational principle, you can derive all the Christoffels and write down the geodesic equation. It's a second order ODE, and if you patiently write it down in this coordinate system, this is what it looks like. It's a nonlinear system of ODEs with the second derivatives of each of these components being expressed by the products of the first derivatives with some additional complicated coefficients. So it doesn't look nice in any way, this system. Approaching it directly looks quite unpromising as an approach. There is one important thing we can notice when you look very carefully at these equations, and in particular, what happens, we can notice something if you look carefully at the equations for the theta, the azimuthal angle. Not the azimuthal angle, the theta angle. Namely, it's easy to notice that if we assume that theta initially is equal to pi over 2, so we are at the z equals 0, the body is at the z equal to 0 plane, and also its derivative vanishes there, so the body has a velocity tangential to this plane, then it's easy to check that theta equal to pi over half is a solution of this equation independently of everything else, simply because at theta equal to pi half, this cosine is 0, so this term vanishes. This vanishes because it's the first derivative, this is the second derivative, so both vanish, everything works. What does it mean? It means that if the body is initially at the z equals 0 plane, and the velocity is also tangent to this plane, this thing will remain forever, and the motion of this body will always remain planar. It will always remain at the z equals 0 plane. But here's the important part. Keep in mind that this Schwarzschild solution is spherically symmetric. So this should apply not only to the bodies which are exactly at the z equals 0 plane. When you have a body moving in any way with respect to the central Schwarzschild solution, it is always possible to rotate your coordinate system a little bit in such a way that it is positioned at the z equals 0 plane of the new coordinate system. And also it's possible to adjust it later in order to make sure that the velocity is also tangential. So the motion is always planar. Whatever happens, the body cannot leave this initial plane. And this is a general, typical situation for motion in spherically symmetric situations. If you had a good course of classical mechanics, you probably had you probably solved the problem of motion in a body in a central force, a force which is spherically symmetric, or in a spherically symmetric potential. And you know that in that case, you can reduce the problem to just a planar motion, because every motion is in the end planar with respect to some plane. You can always use the freedom of rotating your coordinate system to make sure that this plane is actually given by theta equal to pi half or z equal to 0. So it's not a mistake to simply get rid of this equation for theta and put theta equal to pi over half. You are not losing any kind of generality this way. And that's a very good thing. It means that we can focus on the equations for t, r, and phi and forget about theta. Is it clear? Do you have any questions? Okay, if not, then yeah, so we can always rotate the coordinate system to make the motion planar in theta equal to pi half or z equal to 0. Now, we have, I told you some time ago that this metric has, the Schwarzschild metric has the property of having 4 independent Killing vectors, the timeline Killing vector, d over dt, the d over d phi vector generating the rotations around the z-axis, plus 2 additional more complicated vectors generating other rotations. Now this means that we'll have 4 conserved quantities. If we define for momentum as the derivative with respect to appropriate affine parameter sigma, then the energy and the 3 components of the angular momentum will be conserved. But that's not the end of the story. Keep in mind that the length of the vector p itself. This is the mass of this test body whose motion we are considering. This also needs to be conserved. So there's also a quadratic constant of motion. And now the idea is to reduce the problem. We'll now perform what you normally do with this type of central force problem. We will reduce the problem to the one-dimensional motion in the radial direction with the help of all of these conserved quantities. We will assume that the motion is planar, so Lx and Ly are equal both to 0. Theta is equal to pi over half, and we only have motion in phi, r, and t with the conserved quantities E, Lz, and m squared. And we will solve the problem, or at least reduce it, or at least give some qualitative understanding of how the geodesics behave based on that. Okay, I think this is enough for this hour. Let's make a break. Thank you very much. Let's meet in 10 minutes. Hello, it's already 10:09. It's time for the second part of the lecture. Let me share the screen. So we are considering geodesic motion in the Schwarzschild metric. This is the metric itself and its inverse, which I have written here just for reference. We are considering only the planar motion, so theta is equal to pi over half and is constant. We get rid of theta motion entirely. The motion happens in tr and phi. X mu of sigma, where sigma is the defined parameter, is our geodesic. P mu is the derivative. We identified with the for momentum. The idea is to reduce the problem to a one potential motion for the radial coordinate using the conserved quantities which come either from the killing vectors or from the conservation of the length of p. And now we'll proceed with the calculations. So the first step is to simply express this p mu using the derivative d r over d sigma, so the first derivative, and the energy and the angular momentum. So we know that minus m squared, that's p mu over p mu g mu u, and that's let's write it slowly. That is minus 1 minus 2 gm over r e naught squared plus 1 minus 2 gm over r minus 1 p1 squared, but we can just write it as dr over d sigma squared plus, let's make a dividing line here, plus r squared multiplying, this is 1, so we get just p3 squared. But now P0 is nothing but the conserved energy divided by 1 minus 2 gm with a minus sign. So we can write this as 1 minus 2 gm over r, energy over minus energy over 1 minus 2 gm over r squared plus 1 minus 2 gm over r minus 1 dr over d sigma squared plus r squared. And now we want to get rid of p3 squared. That's L over r squared. That's p upper 3. So we can write it as L over r squared squared. Okay, this simplifies a little bit. Here we get minus e squared with this 1 minus 2 gm over r in the denominator plus dr over d sigma squared with the same thing in the denominator plus r, or let's write it over this way, L to the squared over r squared. Okay, so this is equal to that. We multiply everything but by 1 minus 2gm over r. And from that we obtain dr over d sigma squared. This is that term plus minus e squared is this guy over here plus L squared over R squared 1 minus 2g over R is equal to minus m squared 1 minus 2g over R. Okay, we're almost there. Now the next step is simply to bring everything on the onto the other side, and also multiply these things with respect to each other, and we get dr over d sigma squared. This derivation, by the way, works for massive particles with m positive or the massless ones, m equal to 0. Okay, so here we have minus e squared plus L squared over R squared minus 2gm over R to the power of 3. And here we got plus m squared minus 2gm m squared divided by R. And that's supposed to be equal to 0. Okay, and let's move to the next. Last small update. We'll be just writing this in the following form. 1/2 dr over d sigma squared is equal to e squared over 2 minus v of r, where this is called the effective potential. And it has the form of v over r is equal to m squared over 2, a constant which is irrelevant really, but then the next terms are more interesting. Gm m squared over r plus L squared over 2r squared minus gm over r to the power of 3 L squared. Let me check again if I'm not missing a term. M squared over 2 will be here. Then there will be gm m squared divided by r with a minus. Gm squared divided by r with a minus. Then there's the quadratic term with a plus, L squared over 2r squared. R squared over 2r squared. And the last term, it will be minus gm over r to the power of 3. This term has no L squared here when I have written it. Sorry. Yeah, it's easy to make a mistake. Okay. So we've got the effective potential. Obviously, we see that it behaves somewhat differently depending on whether m is 0 or not. If m is 0, then the constant is 0, but constant is not relevant. But we have n1 over r term, which can be or not be there. Let's have a look at the plot of this potential. Yeah, so I have prepared a Python notebook. This is the potential, right? So this is for a massive particle with m equal to 1, and for various values of L. So the potential is a little bit different depending on the value of L you choose. And it turns out that it's not, it is really a fundamental difference in shape. So a common feature of all these potentials is that if r is very small, it tends to minus infinity. So in the very end, there's no infinite potential barrier. The particle can, if it has sufficiently large energy, it can reach any kind of small r. This is in contrast with the Keplerian situation. Let me show you the Keplerian motion. If you make the same plot for the Keplerian motion, the motion in the Newtonian gravity with 1 over r square law force, the effective potential looks pretty much the same for large distances, but for small ones, it always contains an infinite potential barrier. Unless you shoot your body exactly and precisely at a given at a given point mass, you can never, the body will never reach it. It will always bounce off from an infinite potential. But this is not the case for massive particles in the Schwarzschild metric, or at least not generally. For very small L, there's simply no potential barrier. The body can decrease its mass r as much as it can. It can be simply swallowed by the central body. It does not bounce off. If L is large enough, however, a barrier appears, but it's a barrier of a finite size. Even if your body has large angular momentum, sufficiently big energy can overcome that, and the body can enter the black hole. By energy, I mean the energy with respect to angular momentum. You can also say that for fixed energy sufficiently large, it needs to have sufficiently small angular momentum in order to be able to pass over this potential barrier and then fall into the body. So there is no infinite potential that would prevent any particle, that would prevent every particle from reaching very small r equal to m, 2gm, or r equal to 0. If the energy is not large enough, however, there is, at least for some values of the potential, there is a potential barrier, and the body will bounce off. It will appear from infinity, but then it will go back to infinity. So sufficiently big angular momentum will prevent the body from falling into the black hole. Another interesting thing is the problem of maxima and minima of the potential. So any maximum or minimum of the potential, of this effective potential, corresponds to a situation when body has a fixed radius. So it undergoes a circular motion. It's on a circular orbit around the central body. For large r, these maxima look pretty much the same as in the Kepler's case, which is over here. So we've got minima of the potential at increasing distance from the, as L increases, we've got minima of the potential at increasing distances from the center of the mass. And the same happens here, at least for sufficiently large L. However, something interesting happens if L is too small. So first of all, apart from just a minimum around which our body can oscillate, or on which it can simply stay on a circular orbit, there's also a maximum, at least for sufficiently large L. A maximum of the potential, in principle, also corresponds to a possible circular orbit, but this orbit would be very unstable. Any kind of radial velocity the body would obtain from anything, radiation pressure, other orbiting bodies, would sooner or later cause the body to either to escape to infinity or conversely slide back to the black hole or to the central body. So all of these inner circular orbits are highly unstable. These ones are stable though. If the body is perturbed, it will simply oscillate, producing not quite a circular, but rather kind of distorted circular motion. And then the further we are from R, so the larger angular momentum we take, the further this circular orbit appears, and the more our potential approaches the potential of the Keplerian motion. Now there's something interesting happening. It turns out that these two branches of solution of radial motion, the unstable one and the stable one, appear exactly at one single moment at r equal to 6 gm. We will prove this in a second. This means that the stable circular orbits exist only and exclusively down to the value of r equals to 6 gm. And there is no stable orbits, stable circular orbits below this value. You simply cannot further decrease the angular momentum, because in that case you simply lose any maxima or minima. For high angular momentum, in principle, you can try to find a circular orbit with larger angular momentum, but it's obviously unstable. So r equals to 6 gm is known as the innermost stable circular orbit, or the innermost feasible circular orbit, one in which you can leave the body for some time and it will just not fly away because of some small perturbations. So it turns out that if instead of keeping our body using an engine, we try to keep it at constant r using orbital motion, this is in practice only possible down to r equals to 6 gm, not 2 gm. The existence of this type of innermost stable circular orbits is in fact quite important for the theory of accretion disks around neutron stars and black holes. An accretion disk which is not very strongly radiating basically consists of particles on almost exactly circular orbits, but these exactly circular orbits don't really exist past this r equal to 6m, so we expect the disk to terminate somewhere in this area. Okay, let's go back to our calculations. So we are looking for circular orbits, massive particles, dv over dr, that's just gm m squared over r squared, minus L squared over r to the power of 3 plus 3 gm. Oh, by the way, an important point I want to make. An important point is that for the Keplerian motion, we haven't derived it, but for the Keplerian motion, so for the Newtonian gravity, the potential looks in fact quite similar. It simply does not have this constant term, which is irrelevant anyway. And it does not have this highest order term, but it does have these two terms. Sorry, this is m squared. So the difference between these two motions is just in this last term, which fairly quickly vanishes as R goes to infinity, and we recover basically the Keplerian potential, maybe with an additional irrelevant constant. Okay, so differentiating this, we get -3 L squared to the power of 4. Which we can write as one over R to the power of 4 GM M squared R squared minus L squared R plus 3 GM L squared. I will also take this guy out of the calculations. R squared minus L squared over G M squared R plus 3 L squared over M squared. Is this correct? There is no capital M here. Yeah. Okay, and now the idea is to assume that this is 0. This is a quadratic equation. And the solutions are, so let's introduce L equals to L over M. So the angular momentum per unit mass, E equals to E over M energy per unit mass. And then you can show that this is L squared, curly R squared over 2M plus minus 1/2, and we've got the square root of L to the power of 4 over GM squared minus 12L squared. Yes. Okay. That looks a little bit odd. But what is clear is that we have no solutions when this is less than 0. So L4 over G squared M squared minus 12L squared is less than 0, meaning that L squared is less than 12 G squared M squared, meaning that L is less than 2 square root of 3 GM times m. So if the angular momentum is too small with respect to the mass of the particle and the mass of the central body, then there is no orbital motion. There's no circular orbital motion. If L is exactly equal, if L is exactly equal to 2 square root 3 gmm, then we have one solution. And if we plug this in here, it's easy to check that this is equal to 6 gm. So the merging of the two solutions, two branches of the solutions, the stable and unstable one, happens when L is equal to 2 square root of 3 gm small m, and then both R plus and R minus are equal and equal to 6 gm. You can check it by plugging everything into here, but I don't want to do it. This basically explains this behavior over here. If L is too small, there is no place where dV over dr is equal to 0. Then there's an inflection point exactly for a particular value of L, and then there is two solutions for the different values of L. And it's easy to check that for the smaller ones, the motion is unstable. The second derivative is less than 0, and it's stable for R plus. Yeah. Okay, let's talk a bit more about the behavior of R plus and R minus as L goes to plus infinity or to 2 square root 3 gmm. Okay, if L plus goes to plus infinity, obviously the R plus goes to infinity because these two guys are equal in that case, more or less. L to the power of 4 is dominated with respect to L to the power of with respect to this guy. So with L going to infinity, we have R plus approaching L squared over G m equals to L squared m squared G m. And that's basically the Newtonian value, the Keplerian value of this orbit. So the position of the R plus, the stable orbit, is very close to the one predicted by the Keplerian law. On the other hand, when L goes to 2 square root of 3 gmm, R plus decreases and goes back to 6 gm. That's also fairly obvious. What is happening with R minus in that case? That's interesting. So obviously, if L goes to 2 square root of 3 gmm, we know that R minus has to approach 6 gm from below. But what happens when L goes to infinity? It turns out, and you can do it by it takes a little bit more time to prove that. It's a bit of an analysis challenge, but look, we know that the product of R plus and R minus is supposed to be 3L squared over m squared. That's the property of the quadratic function. From that, it's fairly easy to show that when R plus goes to this thing over here, R minus is approaching 3 over gm. So this way we prove that. This way we can prove that R equal to 3 gm is also the limiting value for the position for the radius of the unstable orbit. So do you have any questions to circular orbits around a Schwarzschild black hole for massive particles? Okay, I don't hear any. So obviously the next topic will be massless particles. So photons. Can we have circular orbits for photons? So again, we calculate the derivative of the radial effective potential. dV over dr equal to 0 gives us some kind of equilibrium, stable or unstable point. And for m equal to 0, this is equal to 1 over r to the power of 4. And here we get minus r squared r. And here we have 3gml squared. And this is obviously 0 if and only if r is equal to 3gm. This is a linear function. It has only one root, this equation, which is always equal to 3gm, meaning there's only a circular orbit at r equal to 3gm. And then it's also fairly easy to check that for this case, the second derivative is always negative, so this is unstable. Okay, so we have found there is obviously a maximum in the value of the potential, always attained at r equal to 3gm. Let's go back to the plot. I will show you the plot of the effective radial potential for massless particles. So for L equal to 0, this is a flat function. So with no angular momentum, the particle can move radially the way it wants with no obstacles whatsoever. But if it has an angular momentum, then we actually have a potential barrier, which has a maximum always at r equal to 3gm. Sorry, let me add this. Okay. So we have always a maximum at r equal to 3gm and a potential barrier. So again, photons with insufficient energy with respect to the angular momentum will bounce back and move to the infinity if we shoot them into the black hole. But if the angular momentum is too large, too small with respect to energy, or the energy too large with respect to the angular momentum, they can move past this barrier and fall into the black hole. We can have unstable circular orbits at r equal to 3m, but these are unstable. However, keep in mind that photons which get very close to the black hole, even if they bounce back, because of this potential barrier, will spend some more time close to r equal to 3gm before either bouncing back or moving back to the, or falling into the black hole for into small r. Meaning that they will spend some more time around r equal to 3gm, even if there is no, even if the orbits are unstable there. So r equal to 3gm is sometimes known as the photon sphere. This is because, as you see, the geodesics for null particles directed towards the black hole tends to wind around the black hole around r equal to 3gm before either bouncing off or falling into the black hole. Any questions to this? Okay, I don't hear any. So in that case, we will go to our next topic. And the next topic is precession of perihelion. So precession of perihelion is one of most important early tests of general relativity, and it's still a fairly important one. the idea is basically that, as I mentioned, for large R, the potential, the effective potential is very close to the Keplerian one. So we can easily imagine that the motion of particles will be fairly close to the motion of particles in 1/r field. And we know from the Newton's analysis that in this case, the motion of any bound orbit looks like an ellipse or like a circle, which is a degenerate case of an ellipse. However, there is still this additional term, which will play a role of a relativistic correction, and this term will somehow perturb this elliptic motion. It turns out that the main feature, the main effect of this perturbation is that the ellipse given by this orbit appears to be slowly rotating. Its semi-major axis appears to be slowly rotating together with the rotation of the body. This is known as the perihelion advancement, or the perihelion precession, or the perihelion prograde motion, and it's a feature of general relativity which was predicted by Einstein, and it was important in the sense that it explained an effect which was observed since 19th century but unexplained, namely the anomalous perihelion precession of Mercury. Mercury is fairly close to the Sun. It experiences this term most of all planets, and this term causes an additional precession of the perihelion and aphelion of the orbit. The orbit of Mercury is slightly elliptical, and this semi-major axis is rotating a little bit. Most of this rotation comes from interaction with other planets, but there was an unexplained bit which puzzled astronomers for some time. It turns out that GR very nicely explained this anomalous term by the influence of the effective potential, which made Einstein extremely happy. A small problem is that the derivation of precession of perihelion is somewhat more difficult than the derivation of other early GR predictions, like gravitational light bending or frequency shift. I will try to do it now using a method which I hope will be useful. I'll use a method which which is a bit mathematically tricky, but I think it fairly quickly leads to the result and also is very nice conceptually. So let's begin again by the equation itself. So we know that r prime squared over 2, r prime is the let's do it this way. We know that 1/2 the r over d sigma squared is equal to minus 1/2 1 minus 2 gm over r m squared plus l squared over r squared, or e squared minus m squared over 2 minus l squared to r squared plus gm m squared over r plus gm capital L squared r to the power of 3. And we also know that L, the angular momentum, is r squared d phi over d sigma. And now here's the first thing. This equation gives you the motion, the radial motion, in terms of the affine parameter. So in case of massive particles, this is some kind of rescaled proper time. But we are not so much interested in the motion itself. The problem of perihelion advancement is the problem of the trajectory. So the body starts somewhere here, makes an ellipse, but this ellipse turns out to be not quite an ellipse, and the next minimum of the distance, the next perihelion, appears at a slightly different angle. We can read this off simply from the trajectory of the motion, not from the motion itself. So let's try to derive the equations for the trajectory, or r as a function of phi, by passing the sigma as a variable. So we know that dr over d sigma, it's fairly easy to derive an equation for this. This is dr over d phi times d phi over d sigma, which is dr over d phi. Sorry, this is supposed to be sigma. But d phi over d sigma is just L over r squared. So we know that dr over d sigma squared is equal to dr over d phi squared times L squared over r to the power of 4. It's also a trick we often make in the problem of this Newtonian central force, in the Newtonian central force problem. So we've got this guy over here. We plug it into this equation here. And after some kind of reshuffling of terms, we obtain the following equation for dr over d phi. It's also an equation in a similar type of a similar type, plus 1/2 r squared plus gm m squared. So we just make a substitution, dr over d sigma via dr over d phi, and this thing over here, and just clean up the equation a bit. R to the power of 3 plus e square minus m square over 2l square r to the power of 4. So that's the equation for the trajectory without specifying at what time the particle was at each point, but we don't care about that. And again, it has the form of an equation in a potential. Okay, the next step is to introduce a new variable. We introduce the variable 1 r being equal to 1 over u. So that's a variable which gives you the inverse of the radial component. Okay, I will not bore you with every step of derivation, but you can do it yourself. If you just plug in this new variable, here's the equation you get. U prime, by the way, is simply du over d phi. By the way, this is the same trick which leads to the simplest form of the solution of the Kepler's problem. It's also done exactly using this type of substitution in most of textbooks I know. So in a way, in these coordinates, you can reapply the methods you learned from solving the Kepler's problem, the problem of Kepler's motion, and everything seems to work just fine. Plus gm u to the power of 3. Okay, so again, we have a constant and a potential. But this time, we will undo the first step we did, namely, we have reduced everything to the first order equation, but we can do the opposite, go back to the second order equation, which seems to be somewhat nicer in this particular setting. So we differentiate both sides with respect to phi. This kills this constant over here, but that's not a problem, it's a constant. We can always adjust it for a particular solution, and we get u second derivative is equal to g m squared over l squared minus u plus 3 gm u squared. That's it. For the Keplerian motion, this last term is absent. So this term is absent. And this becomes just an equation of a harmonic oscillator, and we can write down the equation without thinking very much about that. Without this term, this is an equation for a harmonic oscillator with a constant force. And I think everybody knows how to solve that. But here we've got a perturbation, and we have to deal with that. Let's make the last steps towards solving this problem. So I would like to make this problem dimensionless in order to emphasize that this thing over here is indeed a perturbation. So I define P to be equals to L squared over G M squared. So the inverse of that, and this has the dimension of length. It can be measured in meters. And I think in astronomy is known as the semi-latus rectum. It's a property of, it's one of possible measurements of the size of an elliptical orbit. It's not really important what exactly it measures. It gives you some kind of idea about how big this orbit is. So this then becomes 1 over P. And then we introduce W equals to P times U, or U equals to P over W. And in these terms, this equation takes the following form. W second derivative is 1 minus W plus 3 GM over P W squared. Okay, so this guy over here is dimensionless. We can call it epsilon. And it's a number which roughly tells you how big this orbit is with respect to the Schwarzschild radius or with respect to the mass. If the orbit is very big, P is very large, this perturbing term doesn't really matter. And we can solve the equation. So let's, in the final note, do the following. If epsilon is equal to 0, Keplerian limit, we have VW is equal to 1 minus W, second derivative is equal to 1 minus W. So W is simply equal to 1 plus E. And here we can take any sine or cosine, any function, any trigonometric function we want. I will use the cosine because it's customary to use it this way. This means that we assume that the orientation of orbit is particular. And I call the magnitude, the amplitude of these oscillations E. It's a dimensionless parameter, which is called eccentricity in astronomy. And from this, it's easy to get the equation for the and here we have a constant called A, I think. Here we have this constant P. This is exactly the equation of an ellipse, of a perfect ellipse in radial coordinates. The important point is that this is a periodic function of phi with the period of 2 pi. This fact means that the orbit is going to close after 2 pi. So if we start from some kind of minimal r at phi equal to 0, then after phi completes its turn to 2 pi, we will be back again, for example, at the point of lowest r, so at the perihelion. So this describes a closed orbit, a perfectly closed orbit, simply because the period of oscillations in the radial coordinate phi is equal to 2 pi. If this period is equal to 2 pi exactly, then the orbit obviously closes. And in this case, this is actually a perfect ellipse. So if epsilon is equal to 0, we recover the Keplerian ellipse with all its properties, E playing the role of the eccentricity, or how elliptical this equation is. In the next lecture, we will try to look what happens when epsilon is not equal to 0 and how this perturbs the shape of this trajectory. In particular, how the perihelion, or the point of closest approach, changes its position with time. Okay, thank you very much. Have you got any questions? I don't hear any. In that case, I think this is all for today, and see you in a week. We will talk more about the Schwarzschild solution, and we will derive the perihelion shift, the perihelion advancement, and we'll talk a little bit about the R equal to M surface and why it is not a singularity and how we define a black hole. And this will be the end of the lecture. So thank you very much.